Hi Dashers. Today we're covering 7.3 and 7.4. I'm going to quickly cover this section here because you'll find out that we're going to handle this type of work in a different way in Chapter 8. So, if you are going to talk about the force of gravity doing work, then we definitely need to pay attention to which direction the displacement is, right? So the force of gravity is always down. If an object is going up, then the force will be opposite of the direction of displacement. So you can see I've got this 180 degrees here. So we can see, let me move that, that if for this snowboarder, we've got force of gravity here, but their displacement is in the up direction, right? So then there will be that 180 degrees, and so the object will do negative work on that object. The force of gravity will do negative work. Another way to think of it is, if it weren't for the force of gravity, this object could keep going upward at a constant velocity, but there's gravity slowing the boarder down. So they're taking kinetic energy away. And that way you can imagine like a withdrawal of energy from that object. But on the way down, that force of gravity is doing positive work. So the force and displacement line up, and we have the object speeding up as it falls. So then we can imagine that gain in kinetic energy is explained by the positive work. Okay, but what we're going to realize in Chapter 8 is it's pretty difficult to keeping track of, well, okay, is it rising right now? Is it falling right now? So we're going to end up trying to make gravity an internal force in a system so that we don't have to constantly keep track of whether it's on its way up or down. And then we can just call that a different type of energy. So we'll get into that in Chapter 8. Okay, and then the next section is about work done by a spring. And we haven't talked really at all about springs in this class. So first we have to talk about how springs work. And the way they work is that the greater the stretch in a spring, or the more you compress a spring, the harder it is to do that. So it might be easy to stretch at first or easy to squeeze at first, but then the more you displace it, the harder it gets to do that. And so the force exerted by springs isn't constant. So we're not going to be able to use our easy formula for work anymore. It's also important to know that springs would like to always return to their relaxed state. Okay, so everybody's experienced this. You can stretch your slinky out, and it's going to want to, when you let go, come back to where it was. And so if you attach something on the end of a spring, it will drag that object along with it. And we call that idea a restoring force, that it will exert a force in the opposite direction that it's, if you've stretched it out, it's going to try to pull anything attached to it back to its unstretched state. If you've compressed it, okay, then anything attached to it is going to want to bounce back out to where it was before. And so what we can see here in your book was that the formula for the force a spring exerts has that direction built in, okay, because it has a negative sign. to show that the force is always going against the way it's been displaced. So here you can see the displacement, okay? Sometimes you don't see the delta sign. I think like on your formula sheet, it might just say X instead of delta X. And then the K is a measurement of how stiff that spring is. So that's called the spring constant. So we have the negative sign representing the direction of the force. So if X is to the right, you can see on this diagram that the spring force is to the left. And that negative sign is there to remind you of that. If it's being compressed here, like in diagram C, okay, then X is a displacement to the left of where its relaxed state is, and then the force of the spring is to the right. Okay, if we look at this graph here, here we're seeing like an absolute value of the spring force, and it's asking you to which spring is stiffer, and then to calculate the K value. So we'll go over that in class. You can think about that on your own. And then, like I said, since the force isn't a constant, we can't use that nice easy formula to solve for the work anymore. We would need the integral, okay, of force with respect to distance. That's what's on your formula sheet actually as the definition of work. And so if you have a line here, then it's not hard to get the area. You can do area of a triangle. So if they asked you, okay, we're going to stretch spring number 1, 0.1, okay, then you could find this area here using the formula for area of a triangle. Or we can use integrals, and if you haven't done those yet, that is okay. You can kind of imagine undoing the derivative, because the integral is the opposite of the derivative. So you can see here that we've got our force function is negative K. Oops, where did the delta go? So now it's just negative Kx dx, okay? So for every little x, that's what dx means, okay? We're going to take every little piece and find the integral. And so if you can imagine, we just need to find the antiderivative of that, okay? And we have limits here, because these limits are saying like, okay, here's where the spring was stretched originally, and then it got stretched to this final position, xf. Okay, and so then you can imagine, oh, well, this must have been, it's linear now. If it's linear, if the derivative is linear, then the original function must have been quadratic, right? And then there must have been a coefficient in front of it. So, well, it's, K, but there must have also been a 1/2 there. Okay, and then the negative sign explains why we have the xi first and then the xf. Okay, so the idea here, though, the big picture, right, is that when is the work positive and when is it negative? Okay, so remember, the work is being done on something attached to a spring. That's really when we care about it. So what we can think of is, when is the spring causing something to speed up? So for instance, if the block is closer to the relaxed position, that's the first bullet point here, than it was originally, okay, then it's, somebody let go. Somebody had it stretched out or compressed, and then they let it go, and you know that's going to be moving kind of quickly then, right? So some of that energy, and we're going to learn about spring energy, but when you compress a spring or you stretch it out, then you're storing some energy in the form of that compression or that stretch. And then when you let go, some of that energy is going to get transformed into kinetic. Okay. So then the X value is going to be less than it was before. And you're going to have some positive work done there by the spring on the block. We're ignoring the force of the person on the block in this picture right now. Work done by the spring is negative if the block ends up farther away from where it wants to be. Let's switch that around. In other words, somebody's doing work on the spring instead of work being done by the spring. Work is being done on the spring, okay? And that's what's happening then, because like somebody's having to stretch that out. Okay. And then, of course, if the block is, ends up right where it started, then work is done by the spring is 0. Okay. So we'll stop there, and we're going to be doing some problems where we can calculate this or where we can compare one state to another. All right.